So I think it's better if we start. Nidev is a fourth-year PhD student at Berkeley and a member of Bliss and Bear Lab. His focus is on the statistical and computational aspects of adaptive decision-making problems and reinforcement learning. Today, he will present his joint work on nonlinear bandits. And here we give the mic to the Nidev so he can talk about his curious case of nonlinear ridge bandit. Thank you.
Thanks for the invitation and thanks for the nice introduction as well. So today I'm going to be talking about some of our recent work, which is called Beyond UCB, the Curious Case of Nonlinear Ridge Bandits. So this is a bandit problem that I'll talk about. And there's lots of bandit papers out there, and I'll try to tell you why ours is interesting. And so this is a joint work with Yanjun and my two advisors, Jiantao and Kannan. So without further ado, let me get started. And I'll also say if there are any questions at any point, feel free to just interrupt me and unmute yourself and just ask. So what about bandits, right? What is this problem about? It's first of all, it's a problem that has had a lot of impact over the past 50 years or so in various areas. So clearly, reinforcement learning is based on many ideas of bandits, and that's used in robotics. It's used in self-driving cars and many other applications. For example, portfolio design is another area. Recommender systems, adaptive routing. The list is endless, essentially. Yeah. So I'm going to introduce the bandit problem, the general bandit problem, in a little bit of detail, and then tell you about the specific setting we're looking at. So basically, there's a parameter set theta, which captures an unknown parameter on which the reward function depends on. There's an action space A. This is where the learner chooses where to pick actions from. There's a reward function class, and so for picking an action, the learner gets a reward. And basically, there's a time horizon for the problem, which is a number of times the learner picks an action and sees a reward. So it's the horizon or the learning horizon for the problem. And so this stochastic bandit environment, nature chooses a parameter theta star. In this parameter set, this known parameter set, it chooses an unknown parameter theta star. And so there's a reward function f subscript theta star, which is not seen, which is unknown to the learner. But the learner picks an action at every single one of these time steps and observes a random reward. And so you can think about this as observing f of theta star of the action A plus Gaussian noise. And so this is the model that I'm going to be thinking about. And the objective of the learner is to minimize what is called the regret. So if you look at this, the first term is t times max over A of f theta star of A. This is the maximum reward that the learner could have gotten if they knew the true reward function. So this is the best possible reward they could have gotten in hindsight. And the second term, subtracting from that, is what the learner actually got. And so the learner picked a sequence of actions A1 through AT. Not all of them were optimal. Many of them might have been suboptimal. And so if you sum this up over all the time steps, you basically observe a reward scaling. You observe you sort of compute what the learner got, and taking the difference of these two gives you the regret of the learner. Yeah. So a very classical and canonical example is where this f theta of A, the reward function of the learner, takes the form of a linear function. So theta is an unknown parameter, inner product with some feature representation of the action A. And so the reward has a linear structure over here. And this problem was very well studied in the literature. There's a lot of work about the linear bandit problem over the past 20 years or so. So today I'm going to be talking about nonlinear bandits, and what better way to start this talk than to give you an example, right? So today, for starters, let's talk about this reward function that looks like this. So it's a linear function, theta inner product A, but I'm going to raise this to the power of 3. And so the raising to the power 3 makes it nonlinear because, clearly x to the power 3 is not a linear function anymore. And so if you look at what happens as a function of this time t, the time horizon of the problem, you look at the worst case regret of the learner, and you can think about either expected regret over here or even the regret with high probability. It's going to be behaving the same way up to these polylogarithmic factors. So one bound is, sort of d square root t. And this is what you would get if you did not have the raised to the power 3 here. So if this was just a linear banded problem, the right scaling of the regret is d square root t, and that's what you'd see over here. This is the blue curve. On the other hand, there's another curve, which is the linear curve, where the regret scales linearly. And this would be the case until some minimum amount of time t, just because the learner hasn't seen any information or enough information to infer anything about theta. So for some amount of time, the learner is going to be making serious mistake in the actions that they play at every single time. And so for the initial period, the regret will have to scale linearly with t. So the point is, initially the regret scales linearly with t. Eventually, it might scale as this d square root t. And what happens in the middle? What is the exact representation or the form of the regret itself? And so, yeah, so you can actually prove that the optimal regret for this problem, it scales as follows. It scales as d cubed plus d square root t. And so if you plotted this out, until time t gets to d cubed, the regret just scales linearly, because of the min over t. And then beyond that, it starts decaying. It doesn't scale linearly anymore. It starts decaying. And so for some amount of time, the regret really, it increases, but by only a constant factor. So it doesn't change all that much until, you get to time d to the power 4. And that's when the d square root t kicks in, because t is growing sufficiently large that it will, overpower the d cubed term. And so you'll essentially see a regret that scales as d square root t after this point. So it's interesting. There's like some sort of a phase transition that's happening here. You have like some, kink in this function at d cube and something at d to the power 4 and some weird behavior that's going on. And I'm telling you that this is the optimal regret. So this is what the best algorithm would get. If you ignore these polylogarithmic factors, which I'm just claiming they're not significant for now. So what happens is, again, I'm fast forwarding a little bit because this is not something that was known before. This is a result of our work. And so I'll explain to you what's going on here before I justify it to you over the rest of the talk. So this ends up being that there are two phases to the learning process. One is called the initialization phase, and the other is called the learning phase. And so in the initialization phase, the learner really doesn't know what to do. They're just playing sort of bad actions all along. They're getting a very high regret all the way until this time d cube. But that doesn't mean that they aren't learning anything about the problem. And so, yes, the learner is getting a lot of information about theta, even though they aren't playing the best action at this particular time. And at the end of the initialization phase, it will end up happening that the learner will have an action A that is almost, it's, let's say, it's not as good as the best action, but it's at least half as good as the best action. So it's a constant factor away from the best action. After having found this action, the learner, is able to use that to sort of bootstrap and really improve their regret much more rapidly then. So it no longer scales linearly after that point. They're able to use that good action that you have and actually show that the regret scales as, only as something like d square root t. Okay. So I'll pause for a second and ask if there's any questions from anyone about this curve. Don't ask yet how this curve came, because that's what I'm going to be talking about later on. But just about what I'm plotting here, or what are the scale of the parameters, for example. Okay, yeah. So I think what I want to really show from the previous example is there's like a curious phenomena that happens in the nonlinear bandit problem. There's some sort of a phase transition that happens in the regret. So I specifically focused on one example, which is, the linear function raised to the power 3. But this is more general. The phenomena of having a phase transition is more general, and I'll talk about this later. And so, yeah, the initialization phase, the regret grows linearly, and there's a fixed cost because of this. The learner is really playing poor actions at this point. But at the end of the phase, the learner has found a good initial action to start the learning process. And then the subsequent learning phase, the regret does grow sublinearly. It doesn't scale linearly anymore, which is good. And the problem starts looking like a linear bandit problem. At least the regret scaling looks like a linear bandit problem. And so, the bandit learning process really uses this good initial action that you found at the previous phase to improve the learning process. So, yeah, the aim of this talk is really to understand two things. understanding the phase transition, when does the regret become sublinear? The other thing is, what algorithm should we use in the different phases of the learning process, and so, yeah, I'll be talking briefly about all of these things today. So yeah, plan of the talk, I'll talk about our main results first, discuss a little bit about the upper bounds and some lower bounds as well. How do we show that these algorithms are optimal? And then some discussions and extensions. And, like we have done this work, and there's a lot of more work this can lead to. There's a lot of interesting open problems this leads to. And so I'll invite collaboration of any form if anyone finds these problems interesting. Okay, so basically the specific setting that we study is what is called a ridge bandit problem. And you might have gotten this maybe from the title, may not be from the title, but we focus on what's called a ridge bandit problem. So over here, just for simplicity, let's take the parameter space theta as the unit L2 ball. So these are all the vectors that have their L2 norm, let's say, equal to 1. And so, yeah, I guess I should say the unit L2 sphere and not the ball. The action space over here, again, just to keep it simple, because I will discuss the more general setting next. But for simplicity, let's take the case where the action space is actually the L2 ball over here. So it's all the actions which have L2 norm at most 1. And now the specific form of the reward function is called a ridge function. So this is like some nonlinear function f. So previously it was the case f, x cube. This function is applied on the inner product of theta with a. So this is the setting that we study in this, for this problem. And it turns out that a lot of interesting things happen when the reward function has a specific formulation. So yeah, I'll mention a little bit more about the assumptions in this paper and motivate them just a little bit. So the first thing is what's called normalized scale. This is just to make it so that the problem is at the correct scale. It's not too large or too small. And this is just so that we can get a reasonable scaling on the regret. The normalized scale just says that when the argument of this function is 0, the value of the function, so this is a typo, this should be a 0. And when the function value, when the argument is passed as a 1, the function is maximum and it's equal to 1. That brings us to the second assumption, monotonicity. So again, I'm going to assume that the function f is basically monotone, which means that it's increasing on the interval -1 to 1. You can also study the case where f of x is even and increasing. So it's symmetric about the origin and it's increasing on 1/2 of the origin. Let's say the 0 to 1 part. And the implication of this, and really where this comes from, is just noting that you can now characterize what the best action is, right? And so if I tell you that the function f is maximized when its argument is 1, plugging in this action a as theta star, and so theta star is what the true reward function is going to give you the value f of 1, which is again equal to 1, and that's really the maximum reward you can get. So the best reward you can get for this problem is 1, and so the best reward, the cumulative reward in hindsight, is basically exactly t. And the final assumption is what is called local linearity near 1. And you might be curious, I was talking about nonlinear bandits all along. Now, why is local linearity or linearity of any form coming into the picture over here? It's a reasonable question. And so to that, I'm going to say that if you look at the form of this local linearity, what this says is the function f, if you look at its derivative in the interval 0.1 to 1, and you look at the largest derivative in this region and the smallest derivative in this region, they're approximately bounded with respect to each other. So the ratio of the derivatives is not too large, for example. And so this is what it means for the function to be locally linear. This seems like it's still a strong assumption. The thing I would like to mention, though, is this assumption is imposed on this region 0.1, 1. And you can actually change this, and you slightly change the definition of local linearity to make this for x lying in the region 1 minus epsilon to 1. So it's like really a very small interval near 1. As long as it's a constant sized interval, that's okay. It shouldn't depend on d or t or any of the problem parameters. And so that's my justification for saying that the local linearity over here really is not that strong. It's not clear how you get this inner product theta, inner product a. How do you even find actions which have a really good correlation with theta star? How do you get them to lie in this 1 minus epsilon to 1 region, right? Because only then will you be in this linear, locally linear region. If you haven't found such a good action, then you're not in the locally linear region, and it's not clear how you, you know, how do you even get to that particular point? So there's still something pretty non-trivial about this problem. So yeah, the next thing I'm going to talk about is a very brief literature review. And so I'll introduce the special cases of the rich bandit problem that have been studied in the literature. So basically, the first of them is the linear bandit problem, where the function f of x is the identity function. It turns out the optimal regret over here scales as d square root t. And so this is like something that was done, like it was rediscovered many times over the years. And also we have now a very good understanding of the linear bandit problem. And so we see this d square root t regret. Now, if you generalize it a little bit, you can talk about what's called the generalized linear bandit. So this is very similar to the local linearity assumption I mentioned before, except that the local linearity is imposed everywhere on the domain, not just very close to the one point. And so this just says that the derivative is bounded between C1 and C2. You can also relax this and say that the ratio of the maximum and minimum derivatives is bounded by some constants. And so it turns out over here that the regret is exactly the same, the optimal regret. It still scales as d square root t. So it's basically saying that the hardest problem essentially over here is just the linear bandit problem. Then you can talk about what's called the concave bandit problem. So here, when the function f happens to be concave, yet again, it turns out that the linear bandit regret is what is paid over here. The hardest problem instance over here is when f is linear, f is the identity function. And so the regret over here is again the same, d square root t, as you have in the linear problem. Then let's talk about the first nonlinear problem, the simplest one you can come up with, f of x is equal to x squared. This problem is called bandit phase retrieval. And so it's not really clear why you should have the same type of regret scaling as d square root t for this problem. Intuitively, it's not clear why, but it just so happens that there's the same regret scaling. And so I'll touch upon this a little bit later on. It'll become the role of the function f over here and how it affects the regret will become more clear in a little bit of time. And then you can talk about what's called the polynomial bandit, extending the x squared to x cubed, x to the power p. And so what happens over here is you get this optimal regret scaling of d square root t plus d to the power p. So basically, what happens when you have these like general complexity measures? There are like a lot of papers that have been written that propose general complexity measures for these bandit problems. And so one of them is called the decision estimation coefficient by Dylan Foster. And so this work proposes a notion of complexity, and you can compute it for all of these problems. And oftentimes it turns out that the rate that you'd get, the regret rate that you'd get, would be off by a factor of d. Likewise, you can talk about the information ratio. That's yet another parameter. And if you bound these the naive way or the way you know how to, these often don't lead to the right regret dependency on d. So that doesn't mean that these algorithms are faulty. It might just mean that the analysis is not it's not correct. But we don't really have a way of showing that these algorithms work. Okay, so now I'm ready to go to the main results. And I'm going to go somewhat slowly because I think some of these results are slightly dense, especially the ones that involve the function f. It's a sort of complicated looking expression. So I'm going to pause slowly. And if anyone has any questions about why did this come or where does this come from, how do you understand this, I'm more than happy to explain. So first of all, let's talk about coming up with an algorithm or coming up with an upper bound on the regret. So the main result that we have over here is basically, for every function f that satisfies the monotonicity property, it's increasing on -1 to 1, or it's even and it's increasing on 0 to 1. So any function which satisfies this, and it also satisfies local linearity of the function f, there exists an algorithm which achieves the regret which scales as this. Okay, so let's pause for a second and understand what is this upper bound over here. So we look at it, there are two parts, right? So there's like a t square root t part. So this is what, if you go back to the initial plot that I had plotted for the cubic function, this is the second part of the curve where, you've sort of gotten into this d square root t regime. The first, the red, the red number over here, the red integral over here, this is exactly how much time it takes for you to lie in the initialization phase. So it's, if you look at the x cube, it's the part of the function for which you will be in the linear phase of the regret. And so this is the upper bound that you have on the regret. And so the very rough interpretation of this is, what the learner is trying to do in the initialization phase will end up being that they want to come up with an action that has a constant inner product with theta star. And so, if you just think about it, these are all in high dimensions. And so if you pick a random action, it's going to be pretty bad. It's going to not have a constant inner product with theta star. Very high probability its inner product is going to be something of the scale of 1 over square root t, a much smaller number. So it's not really clear whether random actions themselves would just give you this action that has, an inner product of a half, let's say. So if you think about it over here, the integrand x that I'm going to, that you see in this integral, this captures the current progress of the learner. And so you can think about this as like the inner product of theta star with at across the different time steps t. And so initially, when you pick a uniformly random action, which is all you can do when you have no information, you start about at the scale of roughly about 1 over square root t. This is what like a uniformly random action would get you in terms of the progress x. And then somehow at every time step, if you look at this quantity 1 over f prime of x whole square times d square, this is sort of like an SNR or a signal to noise ratio for the problem. And so you sum this up across the various time steps. Until you get to this point where you actually found an action that has a constant correlation. So the best you can get to is x is equal to 1. That's the largest correlation you can get, but it's very hard to get exactly to 1. And so here you're only counting how far you're going until you get to a constant correlation. And like I said, the last phase is the blue curve is when you actually get into the learning phase of the problem and you have d square root t regret. So it's a very rough interpretation of what's going on over here. I'll spend a little bit, I'll come back to this when I'm talking about the upper bound, the algorithm, for example. Okay, so basically now I'm going to talk briefly about the main upper bound, the main lower bound. And so it so happens that you can also prove a matching, approximately a matching lower bound for the minimax regret. And so that if you look at these two expressions, they're slightly different from each other. For example, there's a d square over here, and there's a d over here. And also there's a derivative of the function f prime of x here, whereas there's no derivative, there's just f of x over here. So these two expressions are slightly different from each other. But as it turns out, for many different functions, they will actually evaluate to the same quantity. And loosely speaking, whenever the function f its derivative is smallest around the origin, for example, as is the case with x squared or x cubed or x to the power 4, its derivative vanishes at the origin. Those are the kind of functions for which you'd expect these two bounds to match. Yeah, so the bottom line after showing you both of these results is somehow this fixed cost, the red thing that I've plotted over here, this is the amount of time it takes for the initialization phase to last. This really depends on the entire function f. It depends on the function value at every point from 1 over square root d all the way to a half. So even changing the function at like singular points can significantly possibly change this regret scaling for your particular function f. So I'm going to mention like a side effect actually, or a different result, of which the previous two results were a side effect. It's actually much stronger. It's a bound on the learning trajectory in the initialization phase of the learner. So again, like xt is sort of your progress that the learner is making. And you have like initially at t equal to 0, the progress is around 1 over square root t. This is what a random action would give you. And so if you actually plotted a curve, and so this is like a differential equation that you have over here, it's telling you that the rate of change of x as a function of t is dx squared by dt takes a particular form. And so you can plot this differential equation over here and you get this red colored curve. Similarly, if you try to plot another curve, which is a lower bound curve. So initially, like no matter what you do in the absence of any information, you can't find an action, at least with high probability, that has a better correlation with theta star than a random action. And so the progress initially was also, it's going to be upper and lower bounded by roughly 1 over square root t. And so that's what these two initial points are. And you have another differential equation, which is what corresponded to the other, the lower bound curve. It has a slightly different form. And so the theorem is that there is an algorithm achieving the upper bound learning curve, which means that there is an algorithm such that at every single time step, its progress measured in this form is going to lie above the red curve, which means that it's actually doing well. So you might be confused why I call this upper bound and lower bound when clearly this is the lower bound over here. Well, the upper bound and lower bound just mean that this is what the algorithm achieves. So it's an upper bound on the regret. And the lower bound means that no algorithm can achieve this. So it's a lower bound on the regret. And so the red curve shows that there is an algorithm attaining the upper bound curve, which means that it always lies above this. The blue curve it says that there is, for any algorithm, its learning trajectory will lie below this blue curve, at least with high probability. It cannot ever escape this blue curve or do better than what the blue curve tells you. So it's a very strong result. It tells you that every time step, you're sandwiched between these two curves in terms of the best algorithm's progress. So a couple of quick examples. Polynomial bandit. So this is something that was done before in Huang et al. 2022. And so our result recovers basically the same thing as what they say. The minimax regret scales as d square root t plus d to the power p for any value of p, let's say greater than 2. And somehow it turns out that like many natural algorithms for this problem, eluded UCB and information directed sampling, they pay this extra cost, which scales as d to the power p plus 1. So these two algorithms, at least the best known upper bound for them, scales as d to the power p plus 1. So it's not clear whether they're optimal or not. And it's something I'll talk about later. It actually turns out that one of these two algorithms at least is not optimal. You can show that it's going to be suboptimal. Another interesting problem is called ReLU bandit. And so here the reward function is like f is basically the positive part of x minus 0.1. So this is a bias. And it turns out that you have to pay exponentially many samples to get sublinear regret. And really, it's just because of the fact that until the progress x is less than, it's greater than 0.1, you're going to be seeing zeros at every time step. So you're getting no information until you've really hit a very good action that has, its inner product with theta star. The action's inner product with theta star is at least 0.1. And finding such an action in the absence of getting any information is very difficult. It does really require exponentially many samples. So the last thing is the importance of the function f at every point. This is something I alluded to earlier as well. So if we look at this case where the function f of x is equal to x squared, the fixed cost scales as d squared. And now if you change the function just a little bit, you make it flat, for a little bit of the domain, and then it still scales as, like d square root t, for example. This is still a monotone function. It scales as x squared in this region. So this is still like a monotone function. You can still apply the theorem, but it turns out now that the fixed cost scales as d cubed, even though eventually the function has the same behavior as what it had over here. So this really shows the importance of the function f at every single point. And so, yeah, that's with that I'll end, about the examples. So I'll talk about a little bit about the theorem itself, and how do you get the upper bound? How do you come up with the algorithm? So first of all, the learning phase. Once you found really a good action, a warm start action with this angle, between the action and theta star, at least let's say a half or 0.1 or whatever it is that you want, the learning problem essentially devolves into a linear bandit problem. And why is that so? You can really, say when you can define your warm start action as being the action such that a inner product theta star is 1 minus epsilon. And in that region of the domain, you know that the function satisfies this bounded derivatives. It satisfies local linearity. And so you can apply previously known algorithms for this regime of the problem. And so this is just saying that like once you've really gone sufficiently far enough, the problem becomes linear and you can use the previously known algorithms. But this really doesn't capture the main difficulty of the problem, which is the nonlinear regime. What happens until the point you hit this 1 minus epsilon amount of progress? And if you think about the function f of x being x cubed, you can see here like around 0, the function really is nonlinear. The derivative is going to 0. And so it's not even clear how do you use this, you come up with an algorithm that will make any amount of progress here when the function sort of looks like it's almost 0 here. It's not exactly 0. There is some derivative, it's like as soon as you move a little bit away from the origin, the derivative is non-zero, but somehow the function is very flat around here, and it's difficult to do any form of learning around this point. So like I said, in the initialization phase, the target is to find a good action such that the inner product is a constant. And the algorithmic primitive is very simple. The idea is you find sample a bunch of random actions in a sequential manner, where every action is orthogonal to all of the previous actions. So, A1 through AT, they're all going to be orthogonal to mutually orthogonal to each other. And you keep resampling, so let's say you've sampled A1 through AT minus 1, and you're trying to sample this AT orthogonal to them. You keep sampling this action, randomly until you get lucky. And what it means to get lucky is you've been able to test that the action that you sampled, its inner product with theta star is at least 1 over square root t. And so a random action will satisfy this condition with constant probability. And so you may be unlucky the first time and this won't be satisfied, but if you repeat this, a logarithmic number of times, you will eventually find an action that satisfies this condition. The only thing is you need to certify that this action actually satisfies this property. And so you need to run a hypothesis test to do the certification. And so you keep resampling this action AT until this condition is satisfied. And now if you actually look at this process, so you sample A1, A2, and you keep repeating this for D steps. So you sample A1 through AD. And if you look at this particular action, inner product, the normalized sum of A1 through AD divided by square root D, first of all, this is a valid action because all the AIs are orthogonal to each other. So this is going to be a unit vector, which lies in the action space. At the same time, each of these AIs has, ATs has like a 1 over square root D correlation with theta star. So if you look at this overall vector, you take its inner product with theta star, it's going to be a constant. And so this is really, at the end of the day, all we want to do is find this action. This is what is called as A0. This is the good action, the initial action, and it's being found in a sequential manner. So the hypothesis testing subroutine, this is something I very briefly mentioned over here. You keep resampling until some hypothesis test certifies this behavior. So how do you do this? Let's say you have this action A1, which means that you have like an action which in the progress curve, it's somewhere over here. This is theta star inner product A1. And so the idea is, the idea is once you find an action, like you want to certify that another, like some candidate action A has at least a 1 over square root D inner product with theta star, you can test for the value of the function around this particular point theta star inner product A1. So you simply just evaluate theta star inner product A1 plus A, let's say divided by square root 2. And so if A has a decent size inner product with theta star, you're actually going to make some amount of progress. You're going to find an action that has slightly better inner product. And so, this one line tells you how many samples you require, but even that's not so important. Really, what is important is this test is consistent. Given enough samples, it will correctly give you the answer eventually. Okay, so I'll briefly mention a little bit about the lower bound. And so it just turns out that a lot of new techniques are actually required to get the lower bound to work. And so, we tried many different techniques to begin with, like, in fact, Yanjun, who's on the paper, he's like an expert in proving lower bounds for these statistical problems. So it turns out that, many of these like mutual information based insights. So these are the standard hypothesis testing based lower bounds. These are really not strong enough. They're not able to prove lower bounds on the learning trajectory. It requires new techniques to be able to prove these lower bounds. So basically, we introduced what a new notion of information, which is called chi-square informativity. And so this is very similar to like the KL divergence, for example, or the mutual information, in that if you replace the chi-square divergence over here by the KL divergence, you'd essentially get what is called the mutual information. And so this is a different notion of information. And so you proving bounds, upper bounds on this on this chi-square informativity is sufficient. It turns out it's sufficient to sort of imply a lower bound on the learning trajectory of the learner, or I should say an upper bound on the learning trajectory, a lower bound on the regret. The issue with this is it's not a nice notion of information to deal with. It doesn't satisfy the chain rule or sub-additivity, which both of which are satisfied by mutual information. But somehow we like have a new conditioning based argument that circumvents both of these challenges. And so this really is a new technique, and I think it can have application in many other problem domains where we don't have tight lower bounds. And so if anyone here is interested in lower bounds, I'd encourage you to check out our paper and try to learn more about these techniques. I'm not going to go into it now in the interest of time. So discussion and further questions, last couple of slides. I'm going to talk about suboptimality of UCB. And so UCB is like a very classical algorithm for these bandit problems. And I'm going to focus on what is called Euler UCB, which is a very natural one proposed by Rousseau and Van Roy. The idea is optimism in the face of uncertainty. So at every single time step, you have a confidence set for the parameter theta star, which is sort of shrinking over time. And the action that the learner picks is going to pick the action which has the maximum reward on the best possible parameter in your confidence set, which again is shrinking over time. So hopefully your confidence set always contains the true parameter theta star. And as you sample more and more, hopefully it's shrinking. So eventually this action is going to be theta star. And so if you pick the best action with respect to theta star, you are going to pick the correct action because A is going to be equal to theta star. It turns out that for Euler UCB, you can prove a lower bound. For this specific algorithm, you can prove a lower bound on the regret. And so it turns out that the algorithm requires essentially d over f of 1 over square root d the whole square samples. How do you interpret this? If you look at f of x is equal to x cubed, this shows that Euler UCB actually needs d to the power 4 samples to get to the correct, to get to a constant inner product with theta star. But the optimal thing is d cubed. You have to do something more clever than this algorithm to get to the correct bound. And so that just shows that even though the algorithm is very general purpose, LU to UCB, and it's been shown to work for many domains, and it gives you a general purpose guarantee, the guarantee may not always be optimal. It may be off by some dimension factors, as it is the case here. Another result I'll quickly talk about is online regression. And so this is another line of work by Dylan Foster et al., which proposes what is like called an online regression oracle model. So at every time sequence, there is like, so first of all, to define what is called an online regression oracle, for any sequence of actions AT, this oracle will output an estimate of the parameter theta hat t, such that if you look at the total mean square error, but this is sort of like the online regression error, you're looking at theta hat t inner product AT at every single time t, and you sum the squares of these quantities. It turns out that if this quantity would be upper bounded by O tilde of d, so some dimension dependent parameter. In the online regression oracle model, the learner who is picking these actions only sees the outputs of the online regression oracle. They don't actually see the rewards themselves. So they're getting some limited amount of information and they're choosing actions based on this theta hat. So what it turns out that is even under the oracle model, so this is like a slightly restricted model of computation because the learner only is assumed to get the outputs of the online regression oracle and they can't use the reward function to determine their own actions. So under this model, it turns out that yet again, there's, like there is an online regression oracle, a sort of bad one, if which you use to implement this algorithm would achieve a regret which scales as, d over f of 1 over square root d the whole square. And so this is like a lower bound here. And yet again, it shows you that, this d to the power 4, for example, is unavoidable for all of the algorithms in this family, unless you impose stronger assumptions on the online regression oracle itself. So also just quickly mention that this lower bound extends to offline regression oracles as well. And it's pretty much the same idea that works out over here as well. So these like 3 results essentially are telling you that 3 very popular algorithms for general purpose bandits don't work well for this problem. They get you the wrong regret bound. And I also think that this is sort of the first result of its kind in this level of generality. Like we really don't have lower bounds for any of these algorithms showing that they don't work. And we only have many upper bounds that show that these algorithms work. So I think this is motivating, like looking at these algorithms in a little bit more detail and understanding when do they work and when do they don't. Okay, so the last thing I'll talk about is finite versus infinite actions. So it turns out for the linear bandit problem, having a fewer number of actions leads to a smaller regret. the minimax regret decreases from d square root t to square root d dt log k when there are k actions. So if k, let's say, is d to the power 100, which is a large, but it's still not, it's not exponential in d, the regret bound over here is approximately a square root d factor better. And the intuition is, UCB needs to construct fewer confidence intervals to get the algorithm to work. The question is, does a similar phenomena hold for nonlinear bandits? Does the problem get easier when you have fewer actions? Surprisingly, it turns out that that's not true. That's not always true. So for every link function f, and for k is polynomial in the dimension. So here, if you think about just like d to the power 100 actions, there does exist a rich bandit problem with k arms, such that the regret is 1 over f of 1 over square root d, the whole square. And so if you think about f of x being x cubed, when you had k, let's say they were like at least d cube actions, it turns out that the fixed cost of this infinite action problem is also of the finite action problem is also d cube, which is the same as the infinite action problem. So this improvement phenomena that you see in the linear bandit case is very special to the linear bandit problem. It doesn't generally extend beyond that. And so this is again an interesting result. This wasn't clear a priori, but now we have a better understanding of this. Okay, so I'm going to end now, and just a couple of further questions. It's like one is filling in the gap between the upper and lower bounds. Yes, there is a little bit of a gap between the two. How do we resolve these, this gap? Another thing is analyzing the learning trajectory of a popular algorithm called information-directed sampling. And this is one of the algorithms we weren't able to show a lower bound for. So it's plausible that the algorithm still works as stated, and so can we show that the algorithm does work? And that's one of the questions I think that's pretty interesting. Another question is, what happens if we extend to more general reward functions? So previously we had f applied to a single inner product. What about when you have more parameters, like a sum of, like linear functions, sorry, a sum of ridge functions over here? Can you come up with algorithms for this problem as well? So a quick take-home message, there could be a phase transition in the regret of nonlinear bandits. Traditional algorithms fail to obtain, the correct initialization cost, the fixed cost. At least many of them do. And there's a very interesting dichotomy. The finite action setting exhibits different behavior in the linear versus in the nonlinear bandit. Yeah, and with that, I'll end. And this is our paper. If you want to go check it out later, feel free to. And I'm going to stop now. And if there are any questions, feel free to ask me.
Thank you, Nivet, for your interesting topic and giving your time to us, our audience. And everyone who will see the video of this talk later, if you have any more questions, you can reach Nivet at Berkeley, and also you can read their newest published paper on arXiv that you can see the link here. So I think we're finished here.
Right. I think this is perfect. So I will maybe send you my email or something later. And if you want to circulate that.
Yeah. Okay. I'm gonna include it in the description of the video as well.
Fantastic. Thank you so much.
Thank you. Have a great rest of the day. Bye.
Yeah. Bye.